We're 3D printing vascular grafts. We can actually print these custom grafts for children with congenital heart defects. Over time, that patient's tissue will grow over these grafts and they'll degrade, so you're left with only the patient's tissue and this graft will completely disappear.
Children pose a particularly complex set of problems in that if you're creating a device that's going to be implanted, obviously the child's going to grow. So tissue engineering provides a very nice solution to this problem because you implant a device that's slowly remodeled by the host tissue into living tissue. And then it can easily grow as the child grows in size over the course of years and decades. I was part of the group that helped start the department back in 2005 and 2006. We have faculty and researchers in labs in a variety of different spots on campus. So the establishment of the new building is wonderful because it's going to allow us all to come together and work together in a synergistic fashion.
We've designed a building that has really some of the best equipment, best instrumentation in the laboratories to allow our researchers and to attract the best researchers to College Park.
When we bring people together that have common interests, and those can be mechanical engineering, electrical engineering, materials science, almost all of the departments within the Clark School of Engineering can have a focal point, and that would be human health.
We hope that with all of this work that will make a huge impact on things that will come out. Our students will be the best students educated in this particular discipline, but they will really have a really good impact or significant impact on society.
My laboratory focuses on research in the field of drug delivery, and this has a lot of potential applications in the pharmaceutical arena, impacting patients that take many sort of medicines. And the overall idea is to improve their therapeutic outcome while minimizing potential side effects.
My research group, we develop new technologies that are meant to make medical diagnostics better, easier to use, lower cost, more sensitive, ultimately so that we can perform diagnostics that just simply aren't possible today. One example is bloodstream infections. They often go undiagnosed until the patient actually becomes septic, crashes, and dies within a few hours. So we've been partnering with Canon Life Sciences, a company located in Rockville, Maryland, for the last 3 years. They want to access the minds of the Department of Bioengineering so that they can add new technologies to what they're already doing. It's so important for us to see the technologies that we invent get out where clinicians can actually utilize the technology, patient samples can actually be processed by the technology, and ultimately diagnostic outcomes can be improved. So we certainly hope to use the new building to attract new corporate partnerships.
The building has been built basically from the bottom up to be a hub of activity, to bring people from elsewhere in the Clark School of Engineering, from on the campus, from companies nearby, from the FDA, from NIH, et cetera, all with the idea of trying to inspire new technologies that might improve human health.
We'll have an institute that will have joint appointments, which will invite faculty from the School of Medicine at University of Maryland, Baltimore, faculty from the biosciences to also have appointments in the institute.
UMB is our human health factory, if you will, where the clinicians are there, problems are there, solutions can be brought there. And by working together through Empower, we can do great things. We have established a partnership with Children's National Medical Center, specifically on pediatric devices. It's been awarded an FDA center where we catalyze innovative devices that address pediatric issues specifically.
It is a regional consortium made up of academic centers and industry partners led by Clark School of Engineering and then as well as Sheikh Zayed Institute at Children's National to facilitate medical device development in pediatric space. As a pediatric hospital, we treat children and we teach and then we create knowledge. And then Clark School as an engineering school brings scientific and engineering expertise. So it's a natural marriage to work together to solve pediatric medical problems.
One of the key features of the building is the home of the future Robert E. Fischel Institute of Biomedical Devices. And that will be essentially an incubator of innovative devices, innovative technologies that will have translation into the clinical environment at the University of Maryland, Baltimore, at Georgetown, at Children's National Medical Center, all over the world.
A. James Clark, also known as Jim Clark, has made an incredible difference in our school. Clearly in the world of construction, Clark Construction is known everywhere in the country. He also has a strong interest in the field of biosciences, biotechnology, and bioengineering, biomedical devices. He wants to see enhancements in humanity as it relates to human health, but also he's contributing to his own alma mater and making it have a prestigious signature building so that we can do the great work. And so in every way, he's making a contribution, not just financially.
Bob Fischel is an amazing individual. He created the first drug-eluting arterial stent. He made a stent that actually can open and expand arteries around corners. And one of the things that's most exciting about Bob Fischel is that he gives us his time. He spends time with the students, with the faculty. He lets us understand what people need to move an invention into a clinical marketplace to solve problems.
My projects are mainly focused on autoimmune disease, like multiple sclerosis. So the initial goal is to work on a new therapy to try to generate specific control of the autoimmune reactions in MS, but it could have applications to other autoimmune diseases like rheumatoid arthritis or lupus or type 1 diabetes.
One of the projects we're working on that I think could have an impact on a pediatric population is vaccines for certain kinds of pediatric cancers. We're taking advantage of polymers and incorporating certain kinds of immune signals into these polymeric carriers that could maybe help generate an immune response, but then tell the immune response to be sort of an immunological memory so that once the tumor's gone, you have some mechanism to prevent it from coming back.
One of the things that's most exciting to me personally about building is the integration of all the disciplines that can be brought together to affect betterment of human health.
There's such a diverse number of problems that could all be helped by applying engineering, whether it's imaging or sensing or diagnostics or even therapies like we design for diseases.
What we really want to foster is a collaborative environment of faculty, staff, and students from around the University of Maryland system to work on these complex problems.
In bioengineering, because it is such an interdisciplinary field, you'll be talking to somebody who you thought has nothing to do with your research, and you'll suddenly be able to blend your two ideas together or your two projects together to do something completely new and something that could potentially save lives.
The research in the building will be transformative in the sense that the problems that are addressed are real problems that we all face every day. And one of the things that's great about this building and the catalyst that it will provide is that the people that are engaged will go out and do great things.